Okay, finally we are ready to define or define, is that the right word? Propose, no, define, present the principle of angular impulse and momentum. Let me remind you what the linear version was. So in a linear version, we had L dot equals F, or in integral form, L2 was L1 plus integral of F dt, and this was what we called linear impulse, and L was linear momentum, all of these vectors. So we had these. Now, without going into much details, proof is straightforward, but in the angular domain, we can write h dot about O, the rate of change of angular momentum, equals the moment about that point O, or equivalently in its integral form, h2 is h1, both of these about O, equals integral of m dt, and this is what we call, I don't think we have defined it, angular impulse. And this is the principle of angular impulse and momentum. Let me box it. It is simple, and the beauty of it is that it's very simple. It is very analogous to the linear one. But the angular momentum is a very interesting and weird phenomena. Angular momentum isn't a thing on its own. We derive it mathematically. But as we will see, this derivation, it is just the linear momentum acting at a distance. There's nothing more to that. But this formulation of writing everything in terms of angular momentum actually gives rise to a lot of interesting, well, it can very simply explain a lot of complex phenomena, and we will see a whole lot of examples of those in class. Things that you can the analysis of situations would be very complex in a linear domain, but in angular domain, the solution becomes essentially trivial. So, that is the principle of impulse and momentum. It says the original what is this? This is a plus. The original the original angular momentum plus the angular impulse throughout a time range equals the final angular impulse, or the range, why do I say that? Angular momentum. And the rate of change of angular momentum is the instantaneous moment of a force, or moments about this. Without again going into much details, because the proof is fairly straightforward and similar what we have done before, for a system of particles, system of particles, again, because all the internal forces are collinear and they cancel out each other, we can do the same thing. the total angular momentum of the entire system equals all the external moments acting about that point O, or in the integral form, sum of all angular momentum about point O at later time equals sum of the system's total angular momentum at time 1 plus integral of all external moments, or the external angular impulses. In other words, forget about all the internal forces. Don't worry about those. Only focus on external impulses. And finally, what we have, probably the most useful version of all of these, is conservation of angular momentum, and that is when all external angular impulses are 0. If the integral of this equals 0, then you can assume, or not assume, deduce that angular momentum of the entire system remains conserved, doesn't change. And you have seen this in many situations. The most famous one is these figure skaters that start spinning about their body axis, and as they reduce or fold their arms, they reduce the distances. So distances become smaller. There is no external moment, external impulse on them. So as they reduce the distance, it means the speed must increase, and they spin faster and faster. The total angular momentum remains conserved, and that leads to a change in the spin of the figure skater. And yes, let me see. Oh, one important remark is that similar to the case when we were talking about linear momentum, you could have conservation of angular momentum in different axes. So it is possible that angular momentum about some axes are conserved, angular momentum about some other ones are not conserved. And one other degree of freedom you have when you're dealing with angular momentum is that you can choose point O. So there could be some axes or some points about which the net external angular impulse is not 0, but you can do a different search and find another point or axis that actually has all the external moments equal 0. So you can, you have this degree of freedom. You're allowed to search and explore and find axes that work better for you. Yeah. Let me see. We did this. I'm just checking if I forget anything. We did this. We did this. We did this. Oh, one other thing, now that I have a little bit of space left. Now we have three principles that we can use. We have work and energy principle, work, energy. We have linear impulse and momentum, and we have angular impulse and momentum. And these three, none of them necessitate another one. They are completely independent of each other. It is possible that energy conserved, the other momenta are not. It is possible to have linear momentum conserved, not angular momentum. It is possible to have angular momentum conserved, not the other ones. So they are unrelated to each other. And that actually gives you three separate tools that each one of them may be applicable to a certain part of a problem, and combining them together gives you a whole lot of range, to solve problems. And feel free, and I highly encourage, try to think along the lines of work and energy and linear or angular impulse and momentum and their conservations when dealing with problems. Note which ones which ones are conserved, which ones are not, which ones you can calculate, and so on. So these are very good starting points to think about finding a solution to a problem. So I think that is all I wanted to say. Yeah. And we will see how strong these principles are in solving problems when we see examples in class. So until then, I'll leave you with this beautiful concept. See you.